that many subscribers. I think, by the way, there is a chance that I'm gonna get 100 subscribers. And that comes with the specialty, of course. 100 subscribers specialty. Is it already more than 100? Yes. Oh, that's that's awesome. How many subscribers I have there?
Last time it was 104 or 7.
Whoa! So I made it. I made it. Not 95. So it's not more than 100. Okay. So, but close. It's becoming close. So how it appears. So it's good. All right. So then let's go. Almost there. Just a few more steps. Like, let me see. 2 more steps about this painful trip with Lagrange multipliers. Now, now we looked in a previous slide. We looked like how is a case if we have one function as an original function and one constraint. How is that? What about in m-dimensional case, where we don't have just one function but many functions, and not just the one constraint but many constraints? What happened in that case? Well, the procedure will be all same, so no difference whatsoever. So it's all same. So now what we need to do is that we have to take all the functions and compute the gradients with respect to all the variables. So that we already have. Remember, this is something that is, I'm sure it already rings some bells, because remember, all functions with respect, and I'm differentiating those with respect to my old variables. Jacobian matrix. And there will be something that is also very much, that you're already very much familiar with, and that's this delta f. Now, if I have many functions, this is how you can write it. This is how it goes. And then, there I have my constraints. And then the lambda vector, which is a Lagrange multipliers, is no longer a single scalar value, but it's a vector of unknowns. How many unknowns? Well, equal number of constraints. So, but let's get back to that in a second. And then I'm still accounting the one more information, which is like accounting my original constraints. That's it. Now, this is how I can get those gradients, how I can compute them. So let's look at in the next slide what that means for us. Original function differentiated with respect to our variables. That is generalized forces. Generalized forces that are generalized inertial forces and generalized externally applied forces. And it can be written as it is shown here. My constraints that are differentiated with respect to my variables. What is that? Jacobian matrix. So that's my Jacobian matrix. So finally, I can rewrite my equation of motion such the way that I have here generalized inertial forces, generalized externally applied forces, and my constraints that are count with help of Lagrange multipliers. Was that? This is added because remember this, we look at this, it's coming from this optimization. So that's where it is coming from. This is my original function. This is my Lagrange multipliers and constraints that are differentiated with respect to my variables. That's Jacobian matrix. Now, this comes something that I for sure with 100% certainty. Let me repeat. 100% certainty, I will ask this in written exam. What is the physical interpretation of Lagrange multipliers? Reaction force is due to the constraints. And then that's what it is. What is the, because if going back to that pendulum, in a pendulum I have revolute joint here, so there will be 2 reaction forces. Where are they applying in my system? That will be expressed by Jacobian matrix. Jacobian matrix tells where exactly they are applying, and they are applying in that particular joint, in that particular position. What are their values? What are the numerical values? Because it's obviously having, some force values this direction and this direction those are expressed by Lagrange multipliers. So Lagrange multipliers are reaction forces due to the constraints. And Jacobian matrix is telling where those constraint forces are located in your system. That's what it is. Okay. So now, finally, going back here, I can set this part of the equation to be equal to 0 because actually my reaction forces are accounted because Jacobian matrix and Lagrange multipliers, so I'm good to go. I'm able to express this, I'm able to set this to be equal to 0, but I need this one additional information, which is constraint equations. I need it, of course, because even if you look at the number of unknowns, things are not working out. How can I tell you that? Because if using this equation only, I have too many unknowns versus number of equations. This is unknown, which is a acceleration of generalized coordinates, but this is unknown as well, which is reaction forces. So I simply don't have enough information to solve the response. But I can use additional information, which is my constraint equations. Now things works out. Now I have equal number of unknowns than equations. Equal number of equations than unknowns. Maybe that's the better way to say it. Now, that's it. That's the end of the story. Almost. One more tiny step to take, because this is a set that is called differential algebraic equations. Differential algebraic equations. And they are integrators that can deal with this kind of systems. But actually, when you look at the integrators, what are available out there, many of them can deal with ordinary differential equations, not set of differential algebraic equations. So that's why I'm introducing one more step here. I'm going to convert this one to be expressed by ordinary differential equation. Ordinary differential equation. Okay? So how it goes then? It goes such the way that I'm going to take my constraint equation that is here. I'm going to differentiate that twice with respect to time. And I'm going to call that as a QC. No physical interpretation. It's just because I wanted to do this step from differential algebraic equation to be ordinary differential equations. So I'm calling that as a QC, and that can be expressed like it is shown here. So I'm first differentiating my constraint twice with respect to time. And then this painful component that you are actually familiar with already. You ask it, oh, how is this component? This is what we used in the case of kinematics already once. And then this is a component that we used as well. Now, with this information, I can express my equation of motion like it is shown here. End of the story. I think this deserves a few seconds of silence. Or what? Or explanation. Silence. Because isn't this beautiful? It's all right to cry here. It's feelings are what they are. We can't stop them. This is beautiful moment, isn't it? You just don't see it. But it is a beautiful moment. But let's look what we have here. This is my equation of motion. Let's look at what are the components in the beginning, and then let's look at a little bit about the big picture here. The components that I have here is a mass of my system. That's a block diagonal representation of system mass matrix. And inside of that matrix, you have all the bodies put it in a sub-diagonal form. Clear? Then this guy, that's something that you are very much familiar with. What is that? Jacobian matrix. That you know already. So it's a good friend of you. So So Jacobian matrix. This one here is good friend of you, but with transpose operations, so no special treatment needed. So it's still everything is comfortable. Then 0 here to match the dimension, nothing else. Let's skip this guy, which is our unknowns. Let's get back to that in a second. What is this? This is a vector of generalized external applied forces, expressed in terms of generalized coordinates. Yes, I know it. Makes sense. I'm familiar with that. Very comfortable with that. No problem. Clear? Then quadratic velocity vector. I'm not really a good friend of that, but that's all right, because if setting my body reference coordinate to be center of the mass, it's going to be 0. So it will disappear from your equation of motion. And then this new friend here, which coming when you differentiate your constraint twice with respect to time. Well, it is what it is. You know, everything, there is always have to be that painful guy, painful person in a group. That's it. This is that painful person. Others are friendly persons. No worries. Clear. So let's get back to this guy, this one here. Acceleration of generalized coordinates and Lagrange multiplier. Acceleration of generalized coordinates, what is it we do with that? That we're going to solve. How are we going to solve it? What a big mess. How can I get this, how can I remove all the drawings? Oh, okay. Thank you. So, but what was the story? Oh yeah, it was this guy. This guy. Okay, what did we do here? This is what we wanted to solve. This is our vector of unknowns. This is exactly what we wanted to solve here. How we can solve it? Well, we're going to take this matrix. This is positive definite skew matrix. I can go ahead and invert it, put it in the right-hand side of the equation, and then solve my unknowns. How can I solve it then? Well, I'm going to go and take a look at my vector of unknowns, and this is, once I have my expression of acceleration, then I'm going to integrate to get my velocity. From velocity, I'm going to integrate to get position. That's my configuration. And then I'm going to add my time. I'm going to redo the whole thing. First I'm going to express the acceleration, then I'm going to integrate the velocity, and then I'm going to integrate position. Then I'm going to add more time. Surprising. I'm going to get my acceleration. I'm going to integrate my velocity. I'm going to integrate my position. Clear? What is this one? Lagrange multipliers. What is the physical interpretation of that? No, it's not the color of the body. And it's not even the shape of the body. It's a reaction forces due to the constraints. Reaction forces due to the constraints. That's what it is. Okay, so what do you say? You ready to practice? Ready? Would you like to have some time to think about this, or it's all clear? Okay, let me ask you this. What was control Z? Okay, that's okay. If I have pendulum like this, and if I would solve it by using this equation, how many unknowns I would get to this vector? What would be the number of unknowns? Difficult question, I know that. Still very fundamental question, because it's telling you what are the dimensions in your system. Let's vote. 1 as a number, oh, this is a bit unclear writing. 1 as a number of degrees of freedom. 2 because of 2 global coordinates. 3 because of 3 generalized coordinates. 4 because of 4. 5 because of the generalized coordinates plus constraints. 6 because 2 times generalized coordinates. That's it. So now, so 1, 2, 3, 4, 5, 6. Who is voting for 1? You need to cast your vote. So who is voting for 1? No one? Okay, who is saying 2? No one? Who is saying 3? Okay, now we got some votes. So we got some votes. Okay, 4. Again, no one. 5? Ah. So can I see again? Okay, and 6. No, you cannot vote twice. This is serious vote, like presidential vote. You cannot select, I want to have this guy and this guy. It's not just possible to do it. 5. So it was Adli, I see, and you was also 5. That is correct. 5 is correct. So you can give some credit to yourself. Like really can-do attitude.
Generalized coordinate plus constraint.
2 constraint equations. That's correct, sir. And so it's because of generalized coordinates plus constraint equations. How can I tell you how that's possible? Because here is how many? 3 coordinates. I'm looking at the one body. And I have here how many constraints? 2. So the number of Lagrange multipliers and number of constraint equations, they must match. They must match. How many unknowns in this case? Here is, by the way, a revolute joint. So I have 2 bodies, 2 revolute joints. Options are 10. No other options. So let's all vote 10. So it's 10. How is 10? How come it's 10? Because 2 bodies. How many bodies? How many generalized coordinates for each body? 3. That's that famous song. Remember that gangster rap which says that, everybody have to have 3. Okay? So that's 3 and then multiplied by 2, that's 6. How many constraints? 4. So that's 10. That's how it goes. Okay. So are we ready to practice? Let's look at the summary. So that's where we started. So we introduced the constraints to this equation motion with help of Lagrange multipliers and Jacobian matrix. And then we end up to have set of differential algebraic equations, which we could stop there. But still, I wanted to take one step ahead because I want to convert these set of differential algebraic equations to be expressed by ordinary differential equations. How that was possible? With help of constraint equations. So I differentiate my constraint equation twice with respect to time, and it produced me set of ordinary differential equations where the constraints are accounted. Make sense? Okay, you ready to see something outstanding, really outstanding, something that's going to change your life. So it's life before and after. Ready? You're not ready. I don't care. Let's still take a look. I have in-class quiz here. This coming a little bit of surprise to me too. I thought that I was going to jump to example. So in augmented formulation, this is what we look at. The method based on Lagrange multipliers. Unknowns are acceleration of generalized coordinates, Lagrange multipliers, generalized forces, acceleration of generalized coordinates, and Lagrange multipliers. Would you like me to go back? Or is this is very clear? Very clear. Okay. You sure about this? All of you are sure about this? Now you don't communicate. Is it like this? Okay, good, good. Okay, so let's go. Let's take a look. This one. Next. In augmented formulation, and again, in augmented formulation means method based on Lagrange multipliers. What are the unknowns in that case? There's one option that is very incorrect. Don't vote for that. Please. All right? And then we're going to move on and we're going to look at an example. And that's going to change your life. That's the one that will change your life because we're going to go ahead and solve the response of very complicated nonlinear equation with no problem whatsoever. Okay? And we have plenty of time, so it's really good. And while you're thinking, I got the email from one of the online participants. And in the email, he was asking, how is an exam? Is it going to be the full week that the exam is available? Yes, it is. So the exam will be put on Monday at 00:05. Monday morning. So it's going to be Monday right after midnight. So you can be ready on Monday at 00:05. Then the exam will be on. You can make your first attempt right after that. But now, this is very important you to understand. Because, there is a certain box. You click the box, start the exam. You cannot take it back. You can take it back, but it takes a little bit of effort because you need to invent a time machine, and then you can take it back. But if you don't have a time machine, that's it. So you need to be careful with that. Because sometimes people, let me take a look so then I can go back. And they, oh my God, this was my first attempt and I failed it. Don't do it. So as soon as you click start the exam, that's it. Then it will start. And it start counting. Everything will be accounted after that. Oh yeah, you have 2 hours time. Let me see, 3 hours. I will get back to with the details, but it used to be 2 or 3 hours. So the question was like, if you're allowed to take all the study material with you, you can take whatever material you want. You can use Google. You can use your symbolic math tool. Use your symbolic math tool. Use lecture notes. Use whatever you want, but not your fellow student. This is something that maybe I shouldn't mention it. But we reserve the right to invite some of you to oral exam. And that's what we do. So it's like there are certain triggers in the exam. I don't tell what are those. But some triggers that makes us suspect that there's something going wrong. If we see those red flags in your answers, we're going to invite to have an oral exam with one of the teachers. Could be even me. And if you fail to do it, then the next person you will meet is a rector. Then you can tell your stories to rector. We don't want to hear any explanations. We just don't. I'm sure they are nice and everything, but we just don't want to hear them. Okay.
We can take your help.
Yes. You need to invite me to be with you. I'm ready to help. No, online. So you need to invite me to sit next to your computer. I'm really willing to help you. Okay, so let's go and let's check this. What was another thing that I mentioned that I wanted to say regarding the exam? I just don't remember that right now. But I will get back with the exam details on Monday. All right, so now we're still missing quite a bit of students. Or is it that you guys all done? And the success rate will be, yes, sir. No, 2 attempts. 2 attempts.
Is there any need for registration for the exam?
The question was very important question. 2 questions actually. First one, like how many times you can do your exam? Twice. Highest will be accounted. Also, some of the teachers would like to introduce the rule that the average will be accounted. I don't like that. I feel that it's all right that the highest will be accounted. And another question was that do you need to sign in? Do you need to register the exam? No, you don't. If you have an access to Moodle, you will have an access to exam.
And the second time the exam will be like kind of same or
It's going to be different. Difficult and different. Both. The question was like, how is a exam in second attempt? Is it going to be all the same? No, it's not going to be all the same. So we are, because we have it's all about the lottery. Not all about the lottery, it's all about your knowledge. But there is a question bank. Once you're looking, we see what are the previous questions you have, and then we are selecting the other ones from the question bank. Random selection.
how many questions?
I cannot tell you that, but I'm able to tell you that on Monday, next Monday. I mean. Okay, so the success rate here will be,
80%.
yeah, you're right about that, 80%. 80%, that's how much it's going to be. 80%? 77. Okay, so I was, my hope was not to say generalized forces, because generalized forces particularly are not unknown. We know them, for sure we know them. But what we wanted to solve is acceleration and Lagrange multipliers. That's the vector of unknowns, because look at that. This is trouble here. And I'll go back here. The vector of unknowns is this one. Acceleration and Lagrange multipliers. Okay, now comes the highlight of the course, one of the highlights. And we're going to solve the response of this complicated mechanical system using the skills we just learned. Yes, we're going to make it happen. So we're going to follow the certain steps with no thinking. Remember, very dangerous thing is to start thinking. Don't think. Follow the steps and you will automatically get the equation of motion. Ready to follow it? Let's make it happen. So how is this? Let's look at the mechanism. So this is something that we are very much familiar with. And I would like to apologize that this drawing is a bit misleading, is a bit unclear, because what I wanted to have here is a P with primitive joint. Primitive joint. Not with the one body and then translational joint, but primitive joint. And the Q with primitive joint. So I have here one moving body and two primitive constraints. How many unknowns? Five. Five unknowns. Five unknowns because of three generalized coordinates, two Lagrange multipliers, because of two constraint equations. One that is associated to point P, another one that is associated to point Q. Right, so it's a little small font. Okay, so let's get started. So first we're going to construct the mass matrix. We could do this in a, this very sophisticated way where we are taking the volume integrals over the volume of the body, or alternatively, we could simply use the pre-calculated tables. Either way, well, in real life, use pre-calculated tables because this volume integrals makes no sense. Particularly if you have a random shape of body, it's going to be painful to do this way. But now, so the first component, the mass matrix, is associated to translational components. So I'm simply going to take my mass of the body and put the mass of the body to that 2x2 matrix in its diagonal positions. So here is a mass of the body. Here is a mass of the body. So that's my 2x2 rotation, 2x2 mass matrix. And then the one that is combined, this is the one that is a mass moment of inertia. Mass moment of inertia, let me see, it is simplified such the way that I'm assuming this to be thin body. So I'm assuming that the U bar 2 is insignificant. If you're not comfortable with that, you can do the computing by taking that into account as well. This is how my mass matrix look like. It's a diagonal representation because body reference coordinate system is located in the center of the mass. Here is a mass of the body. Here is a mass of the body. This is mass moment of inertia. This because I'm assuming that this is a thin body. In a thin body, of course, it's not equal to 0, but its effect is insignificant. And that's what they do also in the pre-calculated tables. So when you look at what's the mass moment of inertia of beam-like body, they don't assume that the thickness is significant because it's not significant. Okay, so that's how it appears. That's my first step. My second step, Jacobian matrix. What I need in order to build my Jacobian matrix, my constraints. And then I'm going to differentiate those constraints with respect to my variables. Very mechanical, no thinking. How can I express the constraints? By using the kinematics that I am very much familiar with. So I'm simply going to repeat this equation over and over again, and that helps me to express these constraints. Okay, let's first start with the constraints. So the P point, which is this one here, I need to apologize that font is way too small. Even I have a hard time to see that the P is located up there. But P you can express by using just that kinematics that I'm very much familiar with. So first translation of the body reference coordinate system. Always do it. Always, always. Always you first have to travel the body reference coordinate system, and that's this one. And then you are counting your orientation of body reference coordinate system with help of 2x2 rotation matrix. And then finally, with help of vector U bar, you're traveling the place where the constraint is applying. And this time vector U bar, because the way the body reference coordinate system is here, so let me see if it is visible here. Not really. I need to go back here. So here is more visible. So the X is pointing this direction, Y is pointing that direction. So to go here, vector U bar have to be minus L divided by 2, 0. And that's exactly what is mentioned here. So I'm substituting that information to here, and then I'm constraining. Look, I'm constraining the motion along the global X direction, meaning that this one here have to be equal to 0. All right? So that's my first constraint. I'm going to repeat that again. This time I'm going to constrain my motion in Y direction, and vector U bar will be different too, because constraint is applying in this location. This time the vector U bar is going to be L divided by 2, 0. And it's going to give me a second constraint equation. Look at that. C2, correct. So you notice that immediately when I saw that slide. So it was all clear in the beginning. So typing mistake. So here's my vector of generalized coordinates. So now what I'm going to do is that I'm going to differentiate these two constraint equations with respect to my variables that are Rx, Ry, and angle theta. That's going to be my Jacobian matrix. That's it. Step number 2 is done. Step number 3 is generalized external applied forces. This is going to be simple because, you know, look, the forces that are applying in a system, there is only gravity force that is applying here, and I have some good news. Body reference coordinate system is located in the center of the mass. Helps quite a bit. So how are we going to do this? Well, first of all, the force applying in a global coordinate system is going to be 0 because, you know, the motion in x direction, gravity, is not applying this direction, but is applying this direction. So the component in a global y direction is mass multiplied by gravity constant minus, because downwards. All right? Then where that is applying, it's applying in a point that can be expressed that is shown here. And now, good news. Vector g bar is going to be equal to 0, 0, because it's applying in the origin of the body reference coordinate system. Great. So what is left is this guy here. Now I'm differentiating that with respect to my variables. So what are my variables? Well, generalized coordinates that I'm looked in a previous slide, and it's going to give me the mapping matrix that is very simple in this case. Still is mapping matrix, because I need to convert my forces from global to generalized coordinates. My forces in generalized coordinates are expressed here. Step number 3, done. Step number 4, that's easy. Remember, the mass matrix is a diagonal matrix. Quadratic velocity vector will be equal to 0. Step number 4, checked. Step number 5, well, remember, this non-friendly guy that is almost killing the party. We still have to look at that. We still have to do it, regardless how much we hate this guy. Still we have to do it. But let's do it. So it's very mechanical, so it's not that bad eventually. End of the day, not so bad. Okay, so I know that this guy will be equal to 0, this guy will be equal to 0, because constraints are not function of time. They are not function of time, so that tells me already these two components will be equal to 0. Okay, so first I'm going to take my Jacobian matrix. I'm going to multiply that with the velocity of generalized coordinates. That's give me vector of 2 components. This vector of 2 components will be then differentiated with respect to generalized coordinates. Okay? Let's do it. It's painful, but let's just do it. So what's gonna be the result of that? So this is my vector. I'm differentiating that with respect to my generalized coordinates. Remember, position of generalized coordinates, that's where I'm doing my differentiation, not with respect to velocity. That's why when I differentiate the first equation, only component that is actually affecting is this one, because others are velocities, not positions. So this is what is left. Here, the same thing in the second component. Finally, that is multiplied with respect to velocity of generalized coordinates.
Why is this 1 now? Because we are, it should be 0, 1, 0, 0, 1.
Correct.
It should be 0.
Correct. You're right about that, sir. Because look at the result. You know what is this? That's, again, that evil thing called copy-paste. Don't use it. Never use it in your life, and you will be safe. You're going to go to heaven. Okay? Final thing. Step number 3. Assembly. Assemble work, which you just take the components and you put them in the right location. That's it. Done. Here's mass matrix. Here's my Jacobian matrix. Here's my Jacobian matrix with transpose. Here's my generalized external applied forces. Here's where I got when I differentiate the constraint twice with respect to time. Here is my vector of unknowns. This is what you can tell to computer. Go ahead and solve it for me. You ready to do it? Can we do it? Because I have that example here. Hopefully now this I hope that my MATLAB is cooperating. Let's see. It's coming. It's coming. Okay, good. right, so I'm gonna take this one. No, I'm gonna take this one. I will show the MATLAB code to you next Monday. But what I simply did was that I implemented all these, these matrices and vectors to MATLAB, and I mentioned to MATLAB, go ahead and solve the response to me. And this is how the response looked like. Yes. Yes. You're not dreaming. This is real. This is real. It is really happening. It is really, yes, it is. Yes, it is.
What initial conditions?
What initial condition? Well, with zero initial velocity. With this, let me show it to you. I need to run this again. And why not? Because it's a lot of fun. Isn't this like a best game ever? Pretty much.
Where did the constraints? Was constrained.
Yeah. So here is the first constraint.
Yeah.
Here is another constraint. This green line is, I don't know what it is.
It's actually this.
Okay, look at this. So this is the first and second. Look at this line. Goes up and down. This goes left and right. Here's my man. He said that it's beautiful. Yes, it is. Outstanding. I would say not just beautiful, but almost like half miracle. What do you say? Group hug? No? Okay. Let's close for the day. It's exactly 6. Look at this. So even timing is perfect. Even timing is like absolutely perfect. So next Monday, let's look at this in details and let's see how is a midterm exam. All right. Take it easy and see you on Monday. One more. Yes, sir. One more time. So where is my window? Here. Look at this. Beautiful. These are reaction forces. Look what I'm able to print out here. Reaction forces because of the constraint. Reaction forces because of the constraints. Rotation of local coordinate system. Position of local coordinate system. Beautiful. Okay, thank you and see you on Monday. Oh yeah, and online participants, by the way. It's your once in a lifetime opportunity to see how is a live lecture. Take a full advantage of that.